Welcome to our penultimate lesson in the course on the fundamental theorem of calculus. So last time we discussed the definite integral, which was a way to determine area under a curve. However, we did not have very advanced techniques to actually calculate it. We were just using geometry last time, like area of a triangle or area of a rectangle or a circle. Or you have the limit definition, which we would rather avoid if possible. Well, the fundamental theorem of calculus is a nice way to calculate definite integrals, and it brings in our other type of integral to do so, meaning we're going to use the antiderivative. So let f be a continuous function on the closed interval from a to b. Then if capital F is any antiderivative, remember there's always more than one when you include the plus constant, but it can be any antiderivative, so we choose the most convenient one. If f is any antiderivative of little f, then the definite integral from a to b of f of x dx is solved using this antiderivative capital F. You evaluate at the end points of the interval the limits of integration, and you subtract. And we have special notation for this, which we will use often. Capital F of x, vertical bar, a and b. That just means this difference here. We call this the fundamental theorem of calculus, or FTC. Technically, it's part 2 of the fundamental theorem. There is another part, but we're not really dealing with that in this course. So let's do a couple examples. These are going to be examples that we actually did last time using geometry, but now I'm going to solve it using the fundamental theorem. So part A, you can go back and check to see that we got the same answers. When I graphed this, it was a rectangle. So we use the antiderivative 2x. I don't need to include plus c here because it just has to be some antiderivative. I don't need all of them. So we choose the most convenient one, 2x, rather than 2x plus 1 or what have you. So you plug in the upper limit of integration, 5, minus evaluating at the lower one. Get 10 minus 0, so 10. This one we also did last time, and we ended up getting two triangles, if you recall. One of which was bigger and above the x-axis, and the other one was smaller but below, and that counted as negative. So let's see if we get the same answer. You can go back and check if you want to. Hopefully you took notes. So antiderivative of 4 minus x, the 4x minus 1/2 x squared. Again, I don't need the plus c because any antiderivative will do. So we plug in the upper limit, 6, then minus the whole thing, plugging in the lower limit. So be sure to use your parentheses. We get 24 minus 1/2 times 36 minus -8 and 1/2 times +4 when we square the -2. So 24 minus 18. Here we have -8 minus 2. So 24 minus 18 is 6. And then we have a minus negative, so plus 10. And that is indeed the answer we got last time. You can check or go to the end of the previous video. So, a very convenient method. That is, if you can take the antiderivative easily. Now, that's not always something that we can do with ease. Now, I want to focus on a couple of the assumptions that we made. So, first, I want to focus on why does any antiderivative work? Why don't I need the plus c anymore? And then I'll focus on why does f have to be continuous on this interval? So first question, why any antiderivative? And for the answer, well, let's see what happens when we take capital F of x plus c and evaluate at that difference. So I would get f of b plus c minus the whole f of a plus c. Let's distribute that negative. And look what happens. The c and the minus c cancel. So we end up with capital F of b minus capital F of a anyway. So the plus c really doesn't do anything because it cancels off. So great. When we're using the fundamental theorem of calculus, we do not need to worry about plus c when we take our antiderivatives. Next question. Why must little f, the function we're integrating, be continuous? Specifically on the interval that we care about. But I don't really care about what happens outside of our area of integration. Oh, that's a question, isn't it? Well, let's work this out in a special example. I'll show you why this fundamental theorem fails if you do not have continuity. Let's try the integral from -1 to 1 of 1 over x squared dx. So first we'll apply the formula, and then we'll see that we get an absurd answer. Well, let's rewrite as x to the -2, because then I can use power rule for the antiderivative. And so remember, you will add 1 to the exponent. That'll give me -1, and divide by -1. So that'll just throw a negative in front of it. Don't need plus c here. So I get -1 over 1 minus -1 over -1. Notice here I have a triple negative. So that results in a negative. So I have -1 minus 1, -2. Now, if you look at the graph, you'll see that this cannot possibly be the area. Here's just a rough sketch. You have a vertical asymptote here on the y-axis. Approaching it, going towards positive infinity from both sides. Let's say this is -1 and 1. So I'm talking about this area then. Does that look like -2? No, it's positive. Not only that, it's actually infinite, positive infinity. Although that's not necessarily obvious, you'd have to check that, but it's true. You need methods from Calc too. Don't worry about that too much. My point is that's definitely not -2. That's the takeaway. Here, let's make that a different color. There we go. Looks better. So there's no way that's -2. In fact, it's positive infinity, turns out. So why does this fail? It's because 1 over x squared is not continuous on this interval from -1 to 1. We're undefined when x is 0. So that means you have a little discontinuity there in the middle of the interval. So this means that the fundamental theorem of calculus does not apply. So the conditions aren't met, and we certainly see that we get nonsense. All right, let's discuss some properties of definite integrals. We'll see that there's a lot of overlap with indefinite integrals, but with some new twists. Number one, just like what we had with indefinite integrals, you have this rule where if I multiply by a constant inside, you can just move it on out. K is a real number, like a constant. Obviously, if K were instead something that involved X, like some function of X, then you cannot just move it out. But if K is just a number, then yes, you can move it out like this. Number 2, also, as we had with indefinite integrals, if I'm adding or subtracting two functions and taking their integral, you could treat it as two separate integrals. Take them piece by piece. Excuse me, G. With the same original limits of integration from A to B. Now, the remaining three properties we're going to talk about are new because they only apply to definite integrals because they're dealing with the limits of integration. So for example, if I integrate a function from A to A, the same number, well, that's no real interval at all. It's just condensed to a point. So that's going to give you zero area. It's infinitely thin. There's no width here, so no area. You could also see how this works out from using the fundamental theorem formula. You'd get capital F of A minus itself, so 0. Number 4. If I switch the order of these limits of integration, I'm allowed to do that. It's just that you'll pick up a negative. Now, intuitively, it may seem weird to say put the larger number as the lower limit of integration, but mathematically it works as long as you deal with this negative. So what I like to say with this little comment is that orientation matters. Am I going on an interval from 0 to 1 or 1 to 0? You can technically do both as long as you use a negative when you're going the wrong direction. Number 5. Look at the integral from A to B. Well, we could introduce this number C right here. And split this into two separate integrals. Think of C as like a connector. Maybe I'll highlight. Let's finish writing this. Now, technically, C can be any real number, but it makes the most sense to think of it as a number between A and B. So I've got my full interval. Let's draw an x-axis here from A to B. And C is typically going to be something in between the two. We're just saying that we can integrate here first plus this integral, and you ultimately get the same thing as all the way from A to B. Right? C, technically C can be any real number. Doesn't have to be between A and B, but that's when we're going to use it really. So I'll just say usually between A and B. and this will be useful to us in the coming example. So there are a couple of problems in the homework where Pearson asks you to find an area. Now, typically we associate that with the definite integral. I've been talking that way this whole time, but I am being a little imprecise when I say that. There is this little subtlety that comes in, so we need to be careful. So here's what the problem will look like, at least one of them. Use the definite integral to find the area between the x-axis and the function f of x equals 8x minus 16 on the interval from 1 to 5. And then they add this extra little thing as well, which gives you a big hint as to what's going on. Check to see if the graph crosses the x-axis on the interval. So I'm going to underline that. I'm also going to underline this word area because those are key. So this might seem a little confusing. Why are we talking about the graph crossing the x-axis? Isn't area and the definite integral, aren't those the same thing? And I've been kind of talking that way, but there's a slight difference, actually. The definite integral counts area below the x-axis as negative. And really, when I want to find the area of a region, I technically don't care about being negative. So this keyword area and this phrase here, they're signaling to you that we do not want to count area below as negative. But if I merely took the definite integral, it would. It would count that part as negative. So we need to fix that. So let me just say here, zoom out a bit. Pearson is saying we don't want negative area, quote unquote. When I say I want to find the area, I do not want that to be negative ever. So that's where area is technically a little bit different than the definite integral. Just that little subtlety. I'll draw an arrow to area as well here. There's another problem, I think, where it doesn't spell this part out. And check to see that it crosses the x-axis, but it says find the area, not find the definite integral, but find the area. And that means you're doing this same thing. All right, so first, we will do what this last part says. We're going to check to see if the graph crosses the x-axis on the interval, because that means that we're going to be crossing from negative to positive or vice versa somewhere. And that will be that crucial, important point. So if f of x crosses the x-axis, it will be when y is 0. That's what it means to be on the x-axis. Y is 0. So we plug in 0 for f of x, or y. And then we solve for x. And well, we need to make sure it's in our interval. Otherwise, we don't care. Or this implies you do a little algebra to solve for x, you get 8x equals 16, or x equals 2. Now, is this in our interval we're concerned with? Well, our interval is 1 to 5, so yes. It means we have a point in here where we're crossing the boundary. So that means we're going to have a region below the x-axis and a region above. And if I merely took the definite integral, then we would get the wrong answer because it's going to count that lower part as negative. And I don't want that in this problem. So now that we have a bit of an idea of what's going on, let's sketch a graph. I'm not going to be too precise here, but if I'm graphing y equals 8x minus 16, it means I have a very low y-intercept and a pretty steep positive slope of 8. So let's just make this a rough sketch. Well, we know that this crosses when x is 2. And let's say this is 1 and 5 out here. Actually, let's move the 1 up here. So this means that my lower quote-unquote negative region is first from 1 to 2. But then the one that is for sure positive is from 2 to 5. So again, if I just merely took the definite integral from 1 to 5, then this lower area down here would subtract out of this larger area. And I don't want that for this problem. We want to find total area. That means adding on this little part. Just thinking purely geometrically here. So let's look at that integral from 1 to 5 of f of x dx. And I want to be clear here. This is not the final answer. But it'll help us get there. Now I'm going to use that fifth property we talked about, which means I can take this integral and split it in 2. And I'm going to make this new c x equals 2. Because that's my important turning point in this problem, where we want to treat these integrals separately. So 1 to 2, we have one thing going on. where we're below the x-axis. And then from 2 to 5, we have another thing going on where we're above. So this part on its own is going to be a negative number, and we're going to flip that. So that we get purely positive area in this problem. So to do that, we take the absolute value. Notice I'm not writing an equal sign here because it's not the same thing as what I wrote above. I'm now taking the absolute value, but this is what we want for our answer. We don't need to do anything fancy with this second integral because it's already positive. And now I'm not going to spend time with the fundamental theorem on this point, but if you take that integral and then take the absolute value, you'll get a positive 4. And if you calculate this separately, you get 36. So the overall area is 40. And again, that is counting this lower triangle here as positive. So that gets a little tricky. You just have to find that place where the crossing happens. And that's how you get specifically area, purely positive area. I want to spend the remainder of the time on substitution. There's just a slight complication when you're doing substitution with definite integrals. And I want to add this note. So what's different about this is that you need to be careful with the limits of integration. Those numbers that show up next to the s of the integral sign. Well, the s is the integral sign, that's what I'm saying. So to illustrate, it's a typical definite integral. Well, what I'm not writing, but I could write, is that when I say a here, because x is my variable, I'm dealing with dx, I'm saying a is an x value, so is b. They're x values. That means when I switch over to a new variable u, and I'll have a new differential as well, du, I'm not allowed to use x values here any longer. They need to be u values. So we need to change them. Let's do a couple examples. Negative 2 to 1 2x plus 1 times e to the x squared plus x cubed, that whole expression cubed. Now, we really need substitution in order to do this, in order to take the antiderivative. So the natural choice is some inside function. You might first consider this whole exponent, but the problem is that this cubed here makes things a little complicated. My du won't work out very well. However, if I just take the very inside part, x squared plus x, well, there might be some slight complication from this down the road, but for now, it'll work. So du is 2x plus 1 dx. Notice we see that here in the integral. Right, if I highlight that part, that is du. So this e part will transform into e to the u cubed. I want to think of u as a function of x. I mean, it plainly is, right? U depends on x here, this expression. Well, the reason I'm writing it this way is that I'm going to use this here as a formula to get my new limits of integration. Remember, these are x values. I'm really saying x equals -1, x equals, 1, sorry. And x equals -2. So when I switch the variable, I would give myself a little space here if you're taking notes. When I switch the variable over to u, e to the u cubed du, well, now u is my variable. I need my limits of integration to reflect that. So the way that you do that is that you plug in those old x values into your u expression. So u is x squared plus x. I get -2 squared plus x -2. 4 minus 2, 2. Now we plug in the upper limit, 1. Get 1 squared plus 1, also 2. And that's a bit of a relief, actually, because I would actually still be in a bit of trouble with this integral. I still actually don't really know how to take that antiderivative. But since these limits of integration are the same thing, that makes the picture pretty clear. This must be 0. That was one of our properties mentioned above. I believe that was property 3. Yep. So because we switched over to u, we could see, oh, well, now these limits of integration are the same. So the answer must be 0. Even if I can't calculate this antiderivative, it doesn't matter. Let's do one more involving the square root. integral from 0 to 2, 6 times the square root of 9 minus 4y dy. It would be great to use substitution on this because we have a little bit of a complex expression within a square root. So let's make u 9 minus 4y and see if this works. Means du is negative 4 dy. Well, we don't perfectly see that in this integral. I have dy, of course, but I don't see a 4 out here. Instead, I have 6. Well, we can make this work by throwing in a little multiplier here. Negative 3 halves. If I multiply both sides by that, I'll tell you where I got that from. I want to do that because this is 6. Which would then mean that 6 dy will become negative 3 halves du. Now, how did I know that it was negative 3 halves? Let's use a different color here. That's just a quick little algebra problem. I know that negative 4, that's what I have. I wanted to multiply it by some number, call it x, in order to get 6. Because 6 is what we actually have in the true integral. And that's how I came up with the negative 3 halves. You divide both sides by negative 4. That reduces to negative 3 halves. And you're free to just move that negative up. So that's how I got the negative 3 halves number. Great. So we're just about ready. That 6 dy becomes negative 3 halves du. And this will become the square root of u. That's not too bad. I just have to remember to change my limits of integration to reflect the new variable u. Because right now those are y values. So we plug them into the u expression to get what are these y values now in terms of u. So plugging in 0, get 9. Plug in 2, get 9 minus 4 times 2, so 9 minus 8. That's 1. Now, you need to be careful here. This 9 here, even though it's the bigger number compared to 1, 9 is my lower limit of integration because it came from 0, my original lower limit. So when I transform to u, I actually have to write the 9 down below and the 1 up top, which is a bit unusual, right? Because we normally write the lower number on the bottom, but we had to do it this way. Right, remember, we're picking up a times negative 3 halves, so I'll go ahead and throw that out front. And then, so that basically accounts for the 6. Square root of u du. Now we can clean this up a little bit. Of course, I can write this square root as u to the 1/2, and that will be helpful for finding the antiderivative. Well, I don't necessarily have to do this next part, but it's nice. I could switch the order of these to make 1 on the bottom if I just get rid of this negative. Remember, you can flip the order of those limits as long as you take the negative. That was one of our properties. Property 4, I believe. Yep, property 4 right here. So that's just a nice thing to do to clean this up a bit. It will lead to fewer negatives floating around when you do your calculations. So turning this into a positive 3/2, then from 1 to 9, like we would prefer to have, u to the 1/2 du. And now I can perform power rule on this. Normally I like to write a bracket here, separate off this 3/2. So taking the antiderivative, I get u to the 3/2 divided by 3/2, evaluated from 1 to 9. Notice I'm multiplying by 3/2, and each little term in this I'm dividing by 3/2. These will cancel out. So I really just need to worry about this u to the 3/2. You could include them for a little while and cancel at a later step. This is just more convenient. So 9 to the 3/2 minus 1 to the 3/2. Well, 1 to the 3/2 is always 1. 1 to any power is 1. Well, 9 to the 3/2, think of the half part of the exponent as the square root. So this is the square root of 9 cubed. We could even write an extra step there if we want to. Remember, by exponent rules, I would be multiplying these. That gets me back to 3/2 from the previous step. So the square root of 9 cubed minus 1, that is 27 minus 1. Answer is 26. All right, well, now we have a little break before our exam 3, but then we'll be back for prep week with area between two curves. And that will be the last new lesson